We will develop a mathematical programming formulation to determine the addresses of stock keeping units. But let's start with an example for this problem. Let's assume that our warehouse is given like this. So these grids here represent the individual addresses for stock keeping units. So we will represent these addresses with such grids. In fact, for example, you may have a layout like this and for warehouse, and you may have your dock over here, and then you may have your storage racks designed in this way, and in between them there may be aisles to reach these storage locations or addresses. Okay, so these are racks, and the items, SKUs, are stored over here from both sides, from this side and this side. And in order to reach these addresses, you may need to go through these aisles. Okay, so in this representation over here, we just ignore these aisles and we just say that, for example, if we want to reach this address from this dock, so these are the input-output points. Okay, these are the docks. So, for example, if we want to reach this address from this dock, basically we will use the rectilinear distances unless otherwise stated. So we can go in this way and then in this way. Okay, so and we will assume that the distance of each storage address to each dock is from the center of the address, center of the grid. Okay, and as you see, we have three docks over here, and let's assume that we are going to locate three items, three stock keeping units to this layout, and in total we have 12 locations. So we are finding the addresses of these items for dedicated storage. So in this formulation, we are assuming that we are following the dedicated storage philosophy. What does it mean? It means this. We need to assign these products to these addresses. For example, let's say that we will say that these locations are allocated to item A, then let's say that these are allocated to B and the others are allocated to C. And our objective here is to decide on this allocation. Okay, and of course the objective here when we are making this allocation is to minimize the total travel distance to store these items and to retrieve these items. So in order to store an item A at this address from this door over here is this total distance, rectilinear distance. We are assuming that these docks are points, okay? And from that point to the center of the grid, we will calculate the distance. Okay, so for example, let's say that for this problem, we need 6 locations for A. So this ASA represent the number of locations that are required for stock keeping unit A or product A. For product B, we need SB amount of space, and it is given as 2. And for SC, the number of locations required is given as 4. So in total, if you sum up these values, you see that we require 12 spaces. And if you see, we have 12 grids in this layout. We can number these grids in order to represent them. So for example, this may be storage location 1, this may be 2, 3, 4. Okay, we are just giving these numbers in order to represent them. So 9, 10, 11 and 12. So we will try to find, okay, A is allocated to, for example, 1, and we need, for example, 6 spaces for A. It means that A should be allocated to 6 such addresses. For example, 1, 2, let's say 6, 7, 11, and 12. So in total, this total addresses, number of addresses should be equal to SA value. And when we are making these allocations, another important thing is how many storage retrieval operations each one of these products are making. So these items A, B, and C are different items, and per unit time they may be making different number of storage retrieval operations. For example, A in this example is set to make 20 input-output storage retrieval operations in a given time. What does it mean in a given time? It can be per day, per week, or per year. Okay, 20 input-output operations per year. And then what does it mean? For example, if we assign A to this address to 1, and let's say that it's making storage retrieval operations with this dog 1. So this total distance is 1 plus half over here, 1.0.5 and another 0.5 over here. So the total rectilinear distance is, let's say, 2. We are assuming that in this example the grid length is 1 unit. Okay, 2 unit is the distance. And then we are making 20 such input-output operations per time. So it means that we are traveling these 2 units of distance 20 times in a given time. So in total we are covering 40. We are traveling 40 meters, you can say, per unit time. So we need this information also so that the popularity of the item as well as the distance of the address allocated to this item will give you the metric that we try to minimize. We try to minimize the total traveling distance. On the other hand, as you see in this example, we have 3 different doors, input-output doors. And these doors sometimes are allocated for storage and retrieval operations. So it's said that, for example, this door is only for storage and these 2 doors are for retrieval operations. It can be given in a question like this, and it means that if this is the case, this storage and retrieval operations should be 50%, okay? 50% of the time you are storing, 50% of the time you are retrieving. Otherwise, either you are accumulating items in your storage or you are taking more items than you are storing. Okay, so if this storage operations is 50%, then total retrieval operations must also be 50%. So for example, 30% of these retrieval operations can be on this side and 20% can be on this side. Or sometimes all doors or all dogs are used for both storage and retrieval, so they are not separated as storage and retrieval operations. But it is said that, as in this example, it's said that, for example, 20% of all storage and retrieval operations are performed here, 70% are performed here, and 10% are performed here. So these are given as a percentage, and what does it mean? The summation of these percentages, 20 plus 70 plus 10, should be equal to 100%. Okay? It is the total percentage of storage retrieval operations. Now we are given these data, we want to develop a mathematical programming formulation which will minimize the total traveling distance for storage and retrieval, minimize total distance. And our objective is to, what we try to decide on is to assign products to storage locations. So we are going to develop such a mathematical programming formulation. So in order to formulate this problem, Let's define our parameters of the problem. So we will write the problem parametrically. The first one is Q. Q is the number of storage locations. So for this example, the total number of storage locations is 12. Okay, so Q is 12. The N gives us the number of products. So in this example, we just have 3 products. So the number of products is 3. In other examples, we may have different number of products. M is the number of input-output points. So in this example, we have 1, 2, and 3 input-output points. So M is also 3. Sj gives the number of storage locations required for product A. So S1 is given to us as 6, S2 is given as 2, and S3 is given as 4. So you can write, instead of 1, 2, and 3, you can also write SA, SB, and SC. Okay, it's the same thing. Tj is the number of trips in and out of the storage for product J. Sometimes we call it as the throughput of J. Okay, again for our example, TA was 20, TB was 5, and TC, I don't remember, was 8 or something. Okay, so this is the data. The percentage of travel between each one of these input and output points is also given. So for our case, this P1 with first input output point was 0.2, P2 was 0.7, and P3 was 0.1. And their summation is basically should be equal to 100%. And we also have this dik, which is the distance, or sometimes it is not the distance but the time to travel, required to travel from input output point I to storage location K. So we have how many storage locations? 1 up to 12 storage locations. And how many input output points in this example? 1 up to 3. Okay, now let's have a look at this. We gave these numbers. This was 1, 2, 3, 4. These are the numbers of storage locations. We gave these numbers. Okay, 9, 10, 11, and 12. Now, can you tell me what is the distance between the one, let's say 1. This is input output location 1. This is storage location 1. So basically we are looking at the distance between this input output location and with the center of this first storage location. And if we assume that these grids are 1 meter, okay, then we have 1 plus 0.5 plus 0.5. So it will be 2. D11 will be 2. What about D110? What is the distance? Okay, so the center of the 10th storage location is here, and the distance between the first input output point and this is the rectilinear distance over here, which is 1 plus 1 plus half plus another half, which will make you 3. Okay, what about D26? D26 is the distance between the second input output location and the center of the 6th storage, and basically it is 0.5 plus 0.5 plus 1 plus 1, which is 3. So the distances between each of these storage locations and the input output points can be just calculated by just looking at the layout. Now let's think about formulating this problem. The first thing in formulation is to decide on our decision variable. What should be our decision variable? What are we trying to do? Think about it. We try to minimize the total travel distance, but it is not the decision. It is our objective. In order to achieve that objective, what we try to do? we try to assign each one of these activities to these storage locations. Okay, basically we are trying to decide if product J is assigned to storage location J, storage K, sorry, it will take the value of 1, and otherwise it will be 0. So our decision variable is xjk. Okay, then when we have this objective function, when we have this decision variable, how can we write our objective function? Our objective function is to minimize the total travel distance, right? Okay, then we need to consider each one of these activities. Let's say that A is located to here. Okay, then we are given this pi value. We know this distance, okay, the distance to here, the distance to here, and the distance to here. We all know these distances. And also we know the percentages. So with this input-output door 1, the percentage is 0.2. With this one, the percentage is 0.7. And with this one, the percentage is 0.1. And we know the distances, right? Let's say that this is the distance here is 2. The distance here is 3. And the distance here is 1, 2 again. This is 1, 2, yes. And this is 1, half, and 2, yes. Okay, then only for this storage location, the total travel that we are making is on the average, because we are multiplying with percentages, 0.2 times 2. Okay, 20% of the time we will use this door and we will cover this distance, plus 0.7 times 3 for using the input-output door 2, and 0.1 times 2 for input-output door 3. Okay, so this is the distance if we assign A to this storage location. But the thing is, we also know that for A, we are making in total 20 storage and retrieval operations per time. So this distance is made 20 times. So we multiply basically by 20. Okay. But on the other hand, for A, we need to allocate 6 such locations. Okay. And this one is only one of them. And we will have another from, for example, this, if we allocate A to here as well. Another to here, another here. Not all of these 20 operations will be performed from here. 20 is the sum from all allocated space. So on the average, we will have 20 divided by 6 of these storage and retrieval operations be here. So if we require 6 storage spaces for A, and if we are in total making 20 storage and retrieval operations, then per each one of these storage spaces, we will have 20 divided by 6 storage and retrieval operations. Basically, this is Tj times Sj. Okay, so this is the distance, total distance that we are making if we assign A to this storage location. And what do we have over here? 20 is Tj divided by Sj, right? And this is multiplied by this 0.2 is Pi, the percentage. And this 2 over here is the distance between I and K. Input-output door and storage retrieval operation. But we are summing up this for all input-output doors. So basically that summation is for I from 1 to m. So this value over here corresponds to this summation over here. And we multiply that by Tj over Sj, and this is the distance for one location. Okay, and then we need to sum up for all locations, k from 1 to q. So in this example we have 12. And then we need to take the summation for all parts, because we have written this only for part j, and we have j from 1 to 3 or 1 to n in general. In this example, n is equal to 3. Okay, so we want to minimize this total distance. Okay, Sj Tj divided by Sj multiplied by Pi dik and the summation of all parts, all storage locations, and all input-output doors. This is our objective function. Okay. Then what are our constraints? First of all, at each storage location, so K represents our storage locations and we have Q such storage locations, you cannot place more than one part to a storage location. So it means that J from 1 to n xjk summation should be equal to 1 if the total number of available storage is equal to total number of storage requirement. But you can also write less than or equal to 1. Sometimes the available storage is greater than the required storage. So it means that some of the spaces will be empty. Therefore, you can write less than or equal to 1. On the other hand, for each part A, B, and C, we require a certain number of storage space. For A, we require 6. For B, we require 4, and etc. So, for each part, J from 1 to n, we represented by n, we need to allocate a certain number of storage spaces. So, summation from 1 to q xjk should be equal to the required number of storage spaces. And this xjk is a binary decision variable for all j and k. You see, this is a simple model to solve this problem, but in fact we don't need to solve this problem using such a model. We can find the assignment in an easier way that we will learn. We can have a procedure to assign these storage spaces to these parts. Of course, in your objective function here, you have this cost if this product J is assigned to storage location K. So don't forget to multiply this, otherwise the objective function does not include any decision variables, it's just parameters. Okay, now let's concentrate on this part. Okay, this is the percentage of usage of input-output door I, and this is di is the distance between storage location K and distance from input-output location I. And Pi and dik are both parameters, and we can calculate it initially, and we can rename this as another parameter, which is fk. Okay, then if this is the case, basically we can rewrite our objective function with the remaining terms. So we will make an example to understand what are we doing in this objective function and what is fk in fact. Let's consider this simple example in which we have in total of 6 storage locations. We numbered them as 1, 2, 3, 4, 5, and 6. We have 2 dogs, P1 and P2. We are going to assign 3 products to these 6 slots. And it's said that each dog is equally likely to be used for travel to from these storage locations. So equally likely means that 50% of the time we are using P1 and 50% of the time we are using P2. Number of storage and retrievals for each product is given. For A, we are making 4 storage retrieval operations per unit time per hour. For B, we are making 6, and for C, we are making 3. It means that part B is more popular. It's moving more frequently than the other two. And the necessary required number of storage positions for A, B, and C is given. C requires more space, and B requires less space. The travel times for between the docks and the storage locations for this example is given, so we don't need to calculate anything. And it says that between dock 1 and storage bay 1, the time is 5. So what does it mean? So the distance from here to here is 5 seconds. It's given in terms of time. Okay. Between dock 1 and 2, the distance between here and here, it's 15, and here it's 25. Okay, so all these distances are given. So remember, in our objective, we said that we have this summation for all dogs I from 1 to m, in our case it's 2. We are multiplying this pi with dik. Pi is the percentage, and in this example, the percentages are equal for both of them, 0.5, 0.5. And dik is the distances. Now, we said that we can represent this summation with another parameter, which is fk. So for each storage location, k is the number of storage locations, okay, k from 1 to 6 for this example. So we will calculate for this storage location, we will calculate F1. For this one, we will calculate F2. And for this one, we will calculate F6. Okay, we will calculate 6. So let's calculate F1. What is F1? F1 is, let me erase this part, the percentage from the storage by storage location and the dock, which is 0.5, times the distance between this storage location and this dock, which is 5. Okay, plus the percentage that this storage location makes with the other other dock, which is 0.5, multiplied by the distance between this dock 2 and 1, which is this one over here, 45. Okay, when you make this calculation, it is 25. So F1 is 25. What about F2? Again, for F2, the percentage of this storage location, the percentage of storage retrievals between this location and this dock, which is 0.5, times the distance between dock 1 and storage location 2, which is 15, plus the percentage with the second dock, which is 0.5, times the distance between 2 and 2, which is 25. So when you make this calculation, it should make 20. Similarly, we need to calculate F3, F4, F5, and F6. As an example, let me calculate F6 also to better understand it. So for 6, what do? We take the percentage between 6 and dock 1, which is 0.5, multiplied by the distance between 6 and 1. If the distance is not given, as in this case, you need to calculate it from these grids. Otherwise, use the given values. So between 1 and 6, the distance is 40. Okay, for the second one, the percentage is 0.5 here, and the distance is given as 20. Okay, then the Fk value will be 30. So you need to calculate the remaining ones. Please, as an exercise, do calculate F3, F4, and F5 by yourself. So these are the calculated values. So this is F1, F2, F3, F4, F5, and F6. Okay, so in our objective function, we also have, remember, Tj divided by Sj. So we need to calculate Ta divided by Sa, which is 2, Tb divided by Sb, which is 6, and Tc divided by Sc, which is 1. Now using all these, let's try to write our objective function in open form so we can understand it easily. So for the first one, first product, we have Ta divided by Sa, which is 2, which is 2. Okay, and this is multiplied by Fk, which is 25, and this is multiplied by Xa1. Okay, why is this Xa1? It is Xjk if A is assigned to storage location 1, if it's assigned to the first location. Plus, again, we are continuing with the same product. That's why I'm using the same Ta over Sa. 2 times 20, this is the second storage bay over here. 2 times 20 times Xa2 plus, okay, 2 times 15 times Xa3. Why this is 15? Because now we are considering the third one. And continuing in the same way, for the fourth one, it is 2 times 40 times Xa4 plus 2 times 35 times Xa5 plus 2 times 30 times Xa and 6. Okay, and this is for only item A. But we have 3 parts, we have 3 products, and then we need to continue. For the second one, Tb divided by Sb is 6. So it is 6 times. So I will write all of them in the same, under the same parentheses, because you see we have multiplied by 2 in every one of them. So I will write in common parentheses 6 times 25 times, okay, xb1 plus 20 times xb2 plus 15 xb3, 40 xb4, 35 xb5, and 30 xb and 6. And finally, we have one more for product C, for which TC divided by SC is 1. So it is 1 times 25xC1, 20xC2, 15xC3, 40xC4, 35xC5, and 30xC6. This is our objective function. And when we write our constraints, the first constraint says that we need to allocate only one product to each storage location. So for k equals 1 to 6, this summation of xjk over all j from A, B, and C, okay, this summation should be equal to 1. On the other hand, if we consider the allocation of xa, okay, xa1 plus xa2 plus xa3 up to xa6, we need to allocate 2 of them to product A. For product B, xb1 plus xb2 up to xb6, we need to allocate 6 of them only one of them to B, and I'm continuing on this side, xc1 plus xc2 up to xc6, and we are going to allocate 3 of them to C. Okay, so these are the required number of storage locations. Basically, this is SC, this is SA, and this is SB. So this is our model in open form. If you understand this model, the procedure that we are going to develop will be easier. So in the next lecture, we will develop a procedure to solve this problem. It's very easy. And then we will solve a number of examples.